Astronomers seem to have revealed a puzzling detail in the way dark matter behaves. They found small, dense concentrations of dark matter that bend and magnify light much more strongly than expected. Dark matter is a mysterious, invisible substance that makes up the bulk of a galaxy. The gravitational pull exerted by dark matter is thought to tie galaxies together throughout the universe. There is so much regular matter and dark matter concentrated in massive galaxy clusters that their gravity magnifies and warps light from distant background objects. We call this effect gravitational lensing. We can map where the dark matter is in galaxy clusters by observing how the light bends. Gravitational lensing distorts the appearance of background galaxies into deformed shapes and elongated arcs. Pictures of lensing galaxy clusters are filled with the smeared images of remote background galaxies. The higher the concentration of dark matter in a galaxy cluster, the more dramatic its light-bending power is. Smaller clumps of dark matter associated with individual galaxies in the galaxy cluster create more distortions. In some sense, the galaxy cluster acts as a large lens that has many smaller lenses embedded inside of it. But strangely, astronomers found that 3 galaxy clusters used in their study had concentrations of dark matter that are so massive that the lensing effects they produce are 10 times stronger than originally expected. Hubble's crisp images, coupled with observations from the Very Large Telescope in Chile, helped astronomers produce a more accurate dark matter map. By measuring the lensing distortions, astronomers could trace out the amount and distribution of dark matter. This recent study could signal a gap in our current understanding of the nature of dark matter and its properties. It shows us that there's clearly a missing feature of the real universe that we simply are not capturing in our current theoretical models. With studies like this, astronomers look forward to continuing to pin down the intriguing nature of dark matter to better understand the secrets of our mysterious universe.
Hey everybody, Scott Roberts here from Explore Scientific and the Explore Alliance, and we want to welcome you to the 125th Global Star Party. Tonight the theme is Staring into the Dark. Now, this could have lots of different meanings, but for astronomers, of course, most of us contemplate the universe by staring deep into the sky and trying to just absorb our place in the universe and to explore it, to see all those beautiful treasures that are out there with our telescopes or binoculars or just with the naked eye. It also has to do with the glue that supposedly holds the universe together, and that would be dark matter. And so tonight we've got a great lineup of speakers. They'll try to give their impression of all of this, starting off with David Levy, who will be giving some poetry and some commentary. We welcome back David Eicher from Astronomy magazine, who will be talking about exotic deep sky objects. Chuck Allen from the Astronomical League. Explore Scientific was just at the 2023 Alcon in Baton Rouge, Louisiana, And it was my honor and pleasure to meet up with the National Young Astronomer Award winners. Tonight we have León García, who will be joining us, and his research that did actually get him first place, or tied for first place, was in fact his research into dark matter. So he'll be talking about dark matter and kind of giving you a beginner's introduction. So this will follow up with Astronomy Magazine's Martin Ratcliffe. Martin has done outreach programs probably most of his life, and so we're real honored to have him. This will be a first for both León and Martin on the Global Star Party. Molly Wakeling joins us again with one of her Astronomolly programs. This will follow with Dr. Daniel Barth, who is taking the there is no dark matter stance with the what's called MOND. This is a theory that this is maybe gravity misunderstood. So Maxi Falieres joins us with astrophotography to the max. We've got Marcello Souza from Brazil with us. Cesar Brollo from Argentina down in Buenos Aires, and Adrian Bradley with his beautiful night sky images, and of course John Schwartz in his amazing drawings of the universe. So thank you again for joining us, and we'll get started with David Levy.
Thank you very much. Thank you, Scotty. It is a real pleasure to be here. I remember a few days ago you wrote and asked if I had any thoughts about dark matter, and I certainly do. My passion for the night sky, the reason that I put it above virtually everything else in my life, virtually, not everything, but almost everything else, is that I can see when evening comes. And David Rossiter and I were at our dark side a couple of nights ago, and we could see the Earth's shadow coming up from the east as clearly as we would have from an airplane. And to me, being able to see and the radio astronomers to hear, and perhaps other types of astronomers to feel or even to touch, is what the magic of the night sky is. And also the poetry, which brings us tonight to John Milton. John Milton, when he got his undergraduate degree, he did what a lot of graduates of Oxbridge do, Oxford and Cambridge do when they graduate, and as they go on a trip to the continent. And John Milton very, very much wanted to visit Italy, and he really wanted to visit Galileo, who was still living at the time. And he was told, if you visit Galileo, and you really must, do it before you get to Rome. Because if you do it after you get to Rome, you're not going to let you see him. He's under house arrest, and he's not allowed visitors. So make believe you don't know about that and visit him before you get to Rome, which is what he did. And they talked for hours. And Galileo was really pretty upset because he had just lost his daughter, and letters to father, and David Silva's book about the correspondence between Galileo's daughter and Galileo really are two of her most powerful, powerful books. And so tonight I'm going to quote from John Milton. And while we're listening to it, maybe you might want to think about the dark matter theme of this week. The person who really turned me off to dark matter was Clyde Tombaugh. Right away, he didn't like it. He said, I like things that I can look at. And I totally couldn't agree with him more. And the idea is that he says astronomers tend to take everything they have no idea about, do not understand, and they put it into this dark matter, dark energy box. And I'm really looking forward to listening to the one person who has the opposing theory about dark matter, and maybe I'll learn something about dark matter as well. As a matter of fact, Scotty, maybe I'll be a convert after tonight.
Maybe.
But in the meantime, let's have some Milton. Now came still evening on, and twilight gray had in her sober livery all things clad. Silence accompanied for beast and bird, they to their grassy couch, these to their nests were slunk. All but the wakeful nightingale, she all night long her amorous descants sung. Silence was pleased. Now glowed the firmament with living sapphires, Hesperus, that led the starry host, rode brightest, till the moon, rising in clouded majesty, at length apparent queen, unveiled her peerless light, and o'er the dark her silver mantle threw. Thank you, Scott and all, and back to you.
Thank you so much, David. It's wonderful. It's really fabulous to hear your poetry, your sightings, and to get your take on each time we do Global Star Party. I really love it. Thanks for
Thank
coming
you.
on again,
Thanks, Scott.
David. Yeah. Okay. All right. So we will move on to David Eicher. David has been. David has so many deep interests. He's like one of the guys that I know where I'm just totally amazed at how deep he goes into something. I mean, he is of course so well versed on astronomy, and that could fill someone's whole lifetime in understanding any little facet of what he knows volumes on. But you know, then he's got a passion for history, and you know, and that knowledge that he has could, you know, fill rooms, and I think does fill rooms. And then he's got passions for. He shared with us his mineral collection and his gem collection and his meteorite collection. And again, these are just things that are just they stun me on this. And to know Eicher as I do, he has a lightness about him, a humor about him, and you know, it's all mixed up in this wonderful, wonderful guy. And so, David, I'm glad that you're back on Global Star Party, and that you are back from your tour of the South.
Thank you so much, Scott. And it was so much fun to see you and Martin and David and Chuck and all sorts of people down at the Alcon. That was really a good time we had.
It was fun.
And I encourage anyone who hasn't been to a league meeting to get there, because it is a great, great time. And I think we returned to some normalcy this year with it on the back end of the pandemic here. So I'm going to present to you, just for a change, an object tonight that has a dark matter halo. Sorry, David. But as galaxies do. And if I can share my screen, and I'll share the right aspect of the screen, and I will start a slideshow, and I will talk about yet another object. Can you see HOAG's object, a ring galaxy?
Yes.
Okay, pay no attention to that. It has nothing to do with anything.
Nothing to do with.
But it's completely irrelevant. But what we do want to talk about tonight, we're working our way very slowly south from the North Celestial Pole. There's a really cool galaxy, IC 342, and it's a bright galaxy, but it's extremely heavily obscured because of the dust that is in this part of Camelopardalis. It's a barred spiral, and it would be one of the brighter galaxies in the sky if it weren't behind a whole lot of dust. So it's a kind of an oddball galaxy. It's also face on, so that it has a really low surface brightness. It has a it's about ninth magnitude altogether, but it's large, so it appears faint. Individual parts of it appear faint, in large part because of all the dust in the Milky Way that is in front of this galaxy, in this part of the Milky Way in Camelopardalis. It's large. It measures more than 20 arc minutes across, so 2/3 of the diameter of the moon altogether. But most of it, as I said, is really faint, and it's a nearby galaxy. It's closer than 11 million light years, so really close, and in one of the closest galaxy groups to us. It's nicknamed by some the hidden galaxy because of its delayed discovery of being so faint, its surface brightness being so faint. It's only discovered in 1892, which is pretty remarkable, when a lot of extremely faint index catalog objects were being found in that era, long after most of the NGC was put together. And it is one of the brightest members, as I said. There's a galaxy group called the IC 342 Maffei group, and we'll get to the Maffei galaxies at some point later on, Maffei 1 and Maffei 2, which are much fainter yet and heavily obscured. But this group contains about 18 galaxies, and IC 342 itself is about 75,000 light years across and has about 100 billion stars. So it's a smaller galaxy than the Milky Way or the Andromeda galaxy or M33, even in our own group of galaxies. But it's a relatively robust galaxy as galaxies go, because as we've talked about before, most galaxies are dwarfs, just like stars numerically. So it's a pretty cool object. And if this is this going to cooperate? It's not going to cooperate. Oh dear. There we go.
There we go.
Fifth time on the key was the charm. So here's a field that just kind of shows you the stuff that's around it in this relatively stark area of Camelopardalis. You can see the galaxy there in blue in the middle, and there are, is a Berkeley star cluster and a few other things in the area of some really faint galaxies. But there's not a whole lot going on in this area of the sky. So this is kind of the most interesting object there. And the master, Tony Hallis, has produced this image of the galaxy. And you can see it has a relatively condensed nucleus and a lot of dark matter. Okay, I'm not going to say it. I'll say dark nebulae involved there. I don't want to upset David here. Is he listening still? Okay, no, he's not listening. Okay. Yes,
No,
he is.
okay.
But the dark matter halo, of course, seriously, of this galaxy, as the irascible Fritz Zwicky first raised in 1933, on this scale, of course, would be 3 to 5 times larger than the frame size of this image, way out there, the dark matter halo of this galaxy. And you can see there's some bright and colorful Milky Way stars. And you can see in this image there are a lot of star-forming regions, a lot of H2 regions in this galaxy here, which makes it kind of neat. It's a great object for astro imagers, but it is challenging. If you have a dark sky, in a 12 or a 16 or a 20-inch scope, it looks pretty impressive, this galaxy, but it's pretty faint in small telescopes, as a lot of these challenge objects are. This is a somewhat similar image. It's an older image from Kitt Peak, from the atom block imaging programs at Kitt Peak. That's probably about 15 years old now. The Tony image is pretty new here, but you can see again so much star formation going on in this galaxy, and you can see the barred spiral structure in relatively close to the hub pretty well in this image additionally too. So that's it. That's my weird object, which is actually a pretty bright one overall this week. I'll get to some stranger things in the next few weeks. Again, we have the 50th anniversary of our magazine going on this year with all sorts of special fun. If you want to peek in on Astronomy magazine, I'll mention the latest book that Bakach and I put together that came out last year is this Child's Introduction to Space Exploration, which was a lot of fun to work on. And then I'll mention also we have another meeting coming up now. This is for next spring. Starmus, the 7th incarnation of Starmus, we're going to put together, and we're going to be focusing on Earth. There's a Richard Berry, the fellow who hired me many years ago at Astronomy, used to have a slogan. He said, "Earth is a planet too. We need to pay attention to Earth," which is, of course, absolutely true. So we're going to talk about the future of Earth and how we can take care of the planet that sustains our lives, which is probably in our best interests in the long run. This is going to be in Bratislava, which, believe it or not, is pretty easy to get to, even for Americans who aren't used to traveling around here, there, and everywhere. It's pretty close to Vienna, Austria, which is a major destination city in Europe, of course, and it's going to happen next May. And we have Scott will be involved. David Levy will speak, I believe, at Starmus this time, and I will be doing my usual shenanigans with the Starmus board and with Garrick and Brian May and others. And I think we may get Scott up on there to help us host. Michael Bakich also is someone who helps us host. Some of the days we'll have a lot of rock and roll and a lot of astronauts and Nobel Prize winners and lots of other people talking about all aspects of science, astronomy and chemistry and biology, right on down the line, as well as some rock and roll from Brian and friends. So we hope that you'll join us in beautiful sunny Slovakia next year. So Scott, that's all I have. I will end my show and call it a day and stop my screen sharing. And thank you for having me back. It's been a little bit of an absence with some trips and driving around and, going and photographing Vicksburg and New Orleans and Baton Rouge again. But
I don't know how you fit it all with what you do into your life. It's really, it's stunning, so it's stunning.
And fun to look back in history as well as back in time in the universe as well.
Right. And David was talking about the fun that we had at Alcon. I can't remember a time when
Scott, you beat me to it. From everything I remember, we had a hell of a good time. Yeah, as far as my recollection will take us. And I think Martin could back us up and David on that.
Yeah. Chuck was part of this as well. And Martin Ratcliffe, of course, was part of this as well. And so it was, we had maybe more fun than we actually deserved.
We did. Yes. We'll have to behave ourselves for another year now.
Yeah, that's right. Until the Alcon rolls around again. So.
There you go. Yes, indeed. Yep.
All right. Okay.
Kansas City, I think, is on the horizon.
Yeah, it's right there, and they have the Linda Hall Library
which is one of the if you want to see astronomy book after astronomy book dropped into your lap, each of which is worth $1 million per book. That's a good place to go. That is one of the great collections of astronomy book, as well as other subjects, but astronomy books from the first edition of the Principia, first edition Galileos, all the way through on Earth. It really is an extraordinary collection there.
Yeah, I can't wait, really. Yeah. Maybe Chuck can find a way of moving Alcon up quicker, so we don't have to wait so long. So. Anyway.
Well, you all have me convinced that I haven't lived as an astronomer until I go to one of these conferences.
That's right. You haven't.
Thank you for continuing to sell these things. I got to talk with the wife and make some arrangements.
Oh, it's right in the middle of the United States this time, so there's no excuse.
I should be able to do. There's no excuse. You're right.
That's right.
It is a good time with great people there involved with the league.
That's right. Yeah. And we wouldn't say it unless it was absolutely true. So.
Right.
Oh, I believe in both of you.
All righty. Well, great. Well, thanks, David. And now we are going to move to Chuck Allen. And Chuck was in rare form at Alcon as well. So, so it was a lot of fun having him there. And he was our resident attorney, which apparently we almost needed because we were laughing so hard. So. We were getting some attention, but it was all harmless. We had a good time, and so it was great. Chuck, thanks so much for putting together, being part of the coordination of such a tremendous event. We really should have some of the other people that were, the club that put on Alcon this time, but we do have. León, García, which is very important. And I love that you're on this time. I know that you guys do rotation for the Global Star Parties, but it's very appropriate that you're here at this time because of we get a chance to talk about the National Young Astronomers Award. So I'll turn it over to you.
Great. Thank you very much, Scott. And I was laughing driving home after that conference. Remembering some of the evenings. So it's definitely a great thing to attend. And all of you guys, and made it especially so. I'm going to talk before introducing one of our NIA winners. I'd like to talk about something that starts in darkness and ends in darkness. And I'm going to start with an item. I have an element collection with 95 elements in it. And this is my favorite object. It's a cubic inch of tungsten. Would prefer to have a cubic inch of osmium, but a cubic inch of osmium costs $13,500. And I said, well, I'll deal with a smaller amount of that. But this thing is hefty. It's 0.7 pounds. It's unbelievably hefty. And I'm going to be talking about it a little bit as we talk about density for a moment. So let me share a screen and we'll get on with that. Okay. I assume that's visible to everyone.
Perfect.
As most people know, we've been sending satellite telescopes into space to study the cosmic microwave background, and in particular, the size of the anisotropes in that background to try to determine whether the universe is open, whether it is precisely flat such that parallel light beams would remain so, or whether it's closed, finite and unbounded. And all of our studies within 0.4% margin of error conclude that the universe is flat. That's where it stands right now, but with that margin of error, it could still lapse over to open or closed. But that critical density is amazingly low. The critical density is the average density of the universe. And that density is just about 9 times 10 to the minus 30th grams per cubic centimeter. That's about 5.7 protons per cubic meter. You can imagine something that empty. A cubic meter with less than 6 protons in it on average. That's the average density of the universe. And even more amazingly, perhaps, the visible matter that we see, the baryonic matter that we see, only accounts for about 5% of that critical density, which is why we've been searching for dark matter and dark energy in the universe. Well, on to the tungsten cube. I also have a cube of carbon that's 1 cubic inch and the cube of tungsten. And it turns out it takes nearly 9 cubes of carbon to make up the mass of a cubic inch of tungsten, which is really, as I said, very hefty and kind of shockingly so when you hold it. Osmium is a little bit denser and would be even heftier. Again, I wanted to spill that much money to have a cubic inch of metal. A cubic inch of tungsten has 1 septillion atoms in it. Actually 1.03, but close enough, right? So 1 septillion atoms. That is more atoms than there are stars in the entire observable universe by any estimation.
Wow.
And along one edge of this tungsten cube, 100 million atoms. So if you were hopping from atom to atom, going from one corner to the other, you'd have to hop 100 million times. And that's just the atoms. The particles in the nuclei of these atoms are just pea-sized nuclei sitting in the middle of baseball stadium-sized atoms when you consider the electron shells. So what you have here is an object, this tungsten cube, that is 2 nonillion times denser than the universe is. And yet this tungsten cube is mostly empty space. How much of it is empty space? Here you go. 99.99999999996% empty space. So it's really like a little universe. It has more things in it than there are stars in our universe, and it's mostly empty space like our universe, though not quite as empty. As we move up to something like the core of the sun, for example, we get into something denser. It's about 8 times denser than that tungsten cube in the core. Now, the pressure is unbelievable. The pressure at the center of the sun is about 265 million Earth atmospheres of pressure. That would be the equivalent of taking a submersible to a depth of 1.7 million miles in an ocean, to give you an idea of the pressure that is causing that fusion to occur in the core of the sun. But then we move on to white dwarfs. These, of course, are stellar core remnants following the deaths of stars that lived their lives with generally less than 8 solar masses. As they slough off their outer shells and become planetary nebulae, they leave behind these white dwarfs that are composed of something called electron degenerate matter. This is where the electrons can no longer orbit normally and are pressed into their lowest quantum states around the nuclei of the atoms. There's no fusion occurring in white dwarfs. It's just the residual thermal radiation that comes out of them. The most famous and closest of them is perhaps the PUP, the white dwarf called Sirius B, readily visible in telescopes if you observe Sirius, particularly with an occulting rod or eyepiece. The size of white dwarfs is generally about the size of the Earth, but they generally have the mass of the sun. And the density in the average density in a neutron star is about 1 million grams per cubic centimeter. That means it's about 52,000 times denser than this tungsten cube. And if it were crammed into a cubic inch, it would weigh 18 tons. So that's the average density of a white dwarf. But there are denser things still. There's something called neutron stars that are left over from the collapse of stars that are generally greater than 8 solar masses in size that end their lives in bright type 2 supernovae, which can outshine entire galaxies in which they occur. Indeed, as bright as a supernova is in its ability to outshine a galaxy, that visible energy that you're seeing is only 1/100th of the energy produced by the shock wave of the supernova, and only 1/10,000th of the neutrino blast that results from that explosion. Now, what happens in a neutron star is there's too much pressure, too much gravity for electrons to stay in orbit at all. The protons effectively absorb the electrons and spit out neutrinos and become neutrons. And so you end up with a pure neutron star. And here is a neutron star to scale with New York City. They're roughly 12 kilometers in radius, and they have a density about 800 million times greater than a white dwarf. Now, if we subsumed some material from a neutron star into our tungsten cube, it would weigh 14 billion tons.
Wow.
Give you an example. Now, there are theories that go beyond this. There have been a couple of stars discovered, RX 31856 and 3C58, that are neutron stars that don't seem to match the physics that we expect from neutron stars. RxJ is smaller than normal for a neutron star, and 3C58 is cooler, given the fact that we know it resulted from a supernova just 842 years ago. What some scientists believe is that the neutron stars, these two neutron stars, may have passed through molecular clouds and accreted material that caused them to become even more compressed to form something called a quark star. Now, in a quark star, according to MIT, the bags of quarks, which we think of as neutrons here, get crushed to the point where confinement is lost, and the quarks just form a soup in these quark stars. And when that happens, if we took material from a quark star and put it into our tungsten cubic inch, it would weigh 2 trillion tons instead of 0.7 pounds. There's even a theory that is extremely hypothetical and not well supported, that there may be something called preon stars. These are composed of supposedly the constituent particles that make up quarks. Very few physicists believe that there are such particles. They believe that quarks are indeed fundamental point-like particles. So this is extremely hypothetical and not well supported. But if it did exist, we would be looking at 2 quadrillion tons per cubic inch. In other words, this cube of quark star of preon star material would weigh about 1/3 millionth of the entire Earth's mass. Now, we get to the point where the density becomes so high that we start approaching black hole density. And in the case of the Earth, if we cram the Earth into this size right here, 0.88 centimeters in diameter, it would weigh 9 octillion grams. That's about 300 septillion pounds. and it would become a black hole at that point. And back to darkness we go. And so with that, I would like to turn now to introducing a new friend of mine who impressed me very greatly. And with that, I will return to screen share. And okay, I think we're there.
Yep.
Be nice if it would advance. Okay. As you know, the Astronomical League has had a National Young Astronomer Award now for 32 years. And during that time, we have seen some of the most amazing projects done by young people that you can conceivably imagine. The support we have gotten from Explore Scientific and from Scott Roberts in particular, even when he was with Meade before that, has been a linchpin to the success of this program. Scott came to our support right away in the 1990s, and he's been with us ever since, providing amazing prizes to our winners. Here are our winners posing with the award telescope, which I will show you. It looks a little smaller than it actually is in this picture. I'll show you a better one in a minute. Caitlin Wang is one of our co-winners. She is a senior at the Harker School in San Jose, California, and engaged in the discovery of the smallest ultra short period planets using a novel parallelized phase folding detection system. And she discovered 3 of these ultra short period planets. And to the right, León García, who's our guest tonight, a really wonderful young man seen here with the telescope in the foreground as it should be. It's a fantastic instrument that Scott contributes to our winners each year. And again, we're very grateful to him for his loyalty to this program over so many decades.
Thank you.
I'm sorry?
I said that's very kind, Chuck.
Well, it's also very deserved. And no one more than I knows how incredibly important it's been to this program over the years. León is a remarkable young man. He gave a interview. This is Caitlin doing an interview with Scott in Baton Rouge a couple weeks ago. And León also having a good time talking with Scott as well. And I guess these will be posted at some point.
They are posted now.
They are posted now.
Yeah, León, I've created a web page for León, which I will post in the chat here, and I will be doing the same for Caitlin. And we will embed these videos in there so people can see these interviews.
Fantastic, thank you. León gave a program for us at Baton Rouge entitled Simulating the Dynamics, Collisions, and Morphology of Galactic Ultralight Dark Matter Halos. It was a fantastic program. I don't think I've ever seen a young person give a more relaxed, humorous, and thorough and incredible presentation in my life. And with that, I would like to introduce León García, who is from Corvallis, Oregon, by the way, and will be attending Stanford University next month.
All right. León, it's
well,
all yours.
Thank you so much. That's really high praise. All right. So I'm here today to just give a little bit of a rundown of what dark matter is, what we know about it, what we don't know, and some theories that we have. I'm going to share my screen.
León, you are muted. You are muted.
Sharing. So when I shared it muted. That is unfortunate. Let me just try that one.
You should be able to flip back to the controls and unmute yourself there. Alt tab might get you there.
Thanks, Molly.
There you go.
Huh? One more time, León. There you go.
There we go. That should work a little bit better now.
Perfect.
All right. So now I'm ready to tell you a little bit about dark matter and what it is and how it's played a massive role in shaping the universe's development. So we think that dark matter makes up to 80 to 85% of the universe's mass. And what dark matter is kind of this stuff that we don't know what it is. It's out there in the universe and it does not like to interact with electromagnetic fields. What that means is it's not like you and me. It doesn't emit or reflect light, and it kind of avoids any sort of electromagnetic interactions. And that makes it really, really hard to detect because our way of interacting with the universe is by looking at the light that different things emit. And so that's how we've kind of formed our entire view of the universe thus far. But we know that it exists because of its interaction with things that do emit light. And so that means that it does have some gravitational interactions. This image at right shows kind of how we think that dark matter is distributed over the visible universe. We can't see something like this, but we can perform exhaustive simulations to kind of get the image that's shown here. And what this is a web of dark matter, and the bright areas are showing areas where there's lots of galactic development, and the darker areas are areas where there's basically nothing there because there isn't enough dark matter to provide the gravitational potential energy to form things. And forming things is how we got here today. Without dark matter, we wouldn't be here because primordial gas clouds wouldn't have formed in the early universe, and out of those galaxies and other structures could not have been possible. So we can thank dark matter for all of us being here today, and I'll get to how we know that it is dark matter that's having these effects. So you may have heard earlier today from David Eicher about the concept of a dark matter halo. And what a halo is it's this cocoon of stuff around galaxies that provides this gravitational potential energy, or this gravitational pressure for things to form inside of it, and for galaxies to not rotate out their matter, which I'll get to a little bit later. So these halos are what's fundamentally simulated by different dark matter simulations. And my project was focusing on simulating the halos as opposed to individual pieces of dark matter themselves. And halos extend far beyond the reaches of what we can see for a visible galaxy. For every tiny little galaxy, there's a halo that's extending out potentially tens or hundreds of times larger than the original galaxy itself. So it's pretty big, and there's a lot of matter there that we haven't accounted for. Now, this may anger some other people on the call, but we do know to a certain degree that dark matter does exist in some form, and that it has played a large role in forming many of the structures that we see in the universe today. We know this for 5 main reasons. Number one is this concept of gravitational lensing. The video at the start of this kind of stole my thunder a little bit. This is an image of the Webb Deep Field. It's one of the first images that the James Webb Space Telescope took when it was first pointed into the sky. And it's a very important image because it showcases one of the fundamental phenomena in the universe that supports the existence of dark matter. What gravitational lensing is you get a massive object, you get an object that emits light behind it, and light likes to travel in the shape of the universe, so the light travels around the massive object, gets to us, and it looks lensed or warped, as if we put a fisheye lens around the center of whatever mass it was bending around. And we can actually measure the degree to which galaxies are bent around large masses by using like complex vector operations that I won't get into now. But we do already have a really great way at determining the amount of visible mass through the mass luminosity relation, which is basically we point a telescope at something, we gather the amount of photons, and we know to a great degree how much visible light is emitted to the amount of mass that's there. And generally, when we look at these lensed galaxy clusters across the universe, not just in the Webb deep field, we see that the amount of lensing, or the amount that the light is bent around this large mass, is not actually accounted for by the amount of light that's emitted at the center. So there's too much mass here that light alone doesn't explain. And you can go and look up this phenomenon for yourself of gravitational lensing, micro lensing, and other kind of ways that gravity plays tricks with light that show us that dark matter is playing a big role, because the amount of light that's emitted by structures that we can see isn't accounting for the amount of gravity that's affecting everything else around it. Another way that we've looked at a completely different area of the universe and seen how dark matter has played a really large role is how fast galaxies rotate. Galaxies are generally predicted to rotate according to rotational kinematics, which is the science that Isaac Newton developed in the 1600s. And it's been very accurate at predicting how smaller things like solar systems rotate, where they'll decay as we go further and further out. So this means that things further on the outside will rotate slower, like Uranus and Neptune rotate slower in the solar system than, say, Mercury and Earth, because they're further out. But in galaxies, we don't see this happening. We see things that are way far away from the core rotating very, very fast. And so we think that there is significant mass outside of the galactic core that's causing the galaxy not only to rotate very fast, but these speeds wouldn't make sense, because the stars would be basically flung off at the velocities that they're going, unless there was some mass pulling them to the center that we haven't seen yet. And so that's the observed curve that's shown here in B. And to illustrate this phenomenon is kind of a GIF that shows that on the left, we would expect a galaxy to be rotating like this, where it's basically going very fast in the center, slow on the outsides, but we actually observe this in most large galaxies, where the galaxy rotates more or less the same speed the entire way out. Another way that we've not only been able to determine that dark matter exists, but to put upper limits on how much mass it is in particular galaxy clusters, is by looking at galaxies when they interact and collide with one another. So there are two prominent examples with this, but there are many others that you can look at on your own time. The Coma cluster was the first detection of dark matter, which was one of the forefathers of modern astrophysics. Fritz Zwicky, who was mentioned earlier, was the first to look at the Coma cluster and say, wait, these are moving way too fast to be accounted for by the amount of mass that I can see in my telescope. And so he coined the term dunkel materie, or darkened matter, and he was laughed at by all of his contemporaries. But 70 years later, he's regarded as the original discoverer of dark matter in 1933. And another really great example of how dark matter affects galaxy clusters is shown in the bullet cluster at left. This one's a little bit more nuanced. It's not necessarily that galaxies are just moving too fast to be accounted for by the amount of mass that we see, but more about the distribution of mass that's there. So the parts that are shown in blue here are the areas where we see gravitational lensing occurring. But the areas in red are kind of the areas where gas is emitting light, and we can see the physical mass, or the light emitting mass or baryonic mass of the cluster actually is. And those two aren't matching up. So this is showing us that there are these areas of higher gravitational potential that seem to have passed through each other during this galactic collision that are not accounted for by the amount of light that we see. And so this kind of makes us ask the question, how do we explain gravitational lensing in areas with no visible mass? And the answer is that we can't. Even if we modify the way that gravity moves, we can't fundamentally account for the fact that we are seeing gravitational effects where we have no reason to be seeing them in this collision. I'm hearing some disapproving sounds in the background there, but I'm gonna continue on. The early universe was kind of like a cosmic soup where it was more or less a uniform substance. It was not an incredibly exciting place to be, given that it looked more or less the same everywhere that you looked. But out of that seeming uniformity, there were little bubbles in that soup that emerged, and these are known as primordial gas clouds. The way that we think that they emerged, and we being theoretical physicists, is that there were significant dark matter effects on the early universe that caused early structures like primordial gas clouds seen here to form. And without a force like dark matter causing differentiation in the early universe, we couldn't account for this even if we exclusively looked at inflation, which was the universe being ripped apart in all directions by the force of cosmological expansion. And finally, when we look at the leftover radiation from the Big Bang, which is the cosmic microwave background, and count up all of the little pockets of uniform temperature, which are, by the way, not necessarily that different from one another, we can create this power spectrum shown at right. And this is basically the amount of blobs that are the same size at different temperatures. And we have great statistical analysis that can show us the kind of the effects of dark matter that it would have on the early cosmic microwave background. And when we run different simulations, we've arrived at the 80% number of or mass budget of the universe being constituted of dark matter by just adding more and more dark matter to the simulations. And some people say that it's a fudge factor, but we've seen its effects on completely different areas of physics across the universe and at completely different scales. So a theory of modified gravity, for instance, would have to answer a lot of different questions that dark matter currently is doing a good enough job at answering right now. And so we have a lot of different theories for what dark matter could possibly be. Dark matter could literally be anything, but we have restricted it to a couple different leading candidates. And the reason that we have so many is because we can't see it. And the way that we've had with interacting with the universe has been by detecting the visible light that different things emit and actually being able to quantify different things. But with dark matter, we have to just look at its gravitational effects. So some believe that dark matter could be this weakly interacting massive particle, or a WIMP for short. These particles are almost so large that they are almost macroscopic, and we think that they may weakly interact with electromagnetic fields. And there are a lot of different experiments that we've come up with to try and detect this particle, but for the past 30 years, we still haven't had a detection, which has severely placed some pretty strong upper limits on how much could actually be this WIMP particle. And it's not looking good for this theory currently. There's another theory of what dark matter could be that sits better with a lot of people, that it could be MACHOs, or massive compact halo objects, which is basically saying dark matter is just the stuff that we already know is out there, but we just haven't detected it yet. And so this could be like rogue planets, this could be brown dwarf stars, white dwarfs, neutron stars, and small black holes that we haven't detected. But one of the issues with this theory is that currently we have no way of actually explaining all of the dark matter by just things that we haven't detected yet. So although this could be a significant proportion of the things that we haven't seen, we can't use it to explain away all of this gravitational effect that we haven't been able to kind of determine what exactly is causing it yet. And finally, there are some even stranger theories for what dark matter could be. It could be effects from extra-dimensional space, or it could be some sort of fourth dimension that's interfering with gravity as we know it and is forcing structure formation on the universe. And kind of, we would really have to delve a little bit more into theoretical physics, but that's not and finally, there's sterile neutrinos. A neutrino is a fast-moving particle that's very, very small, and some people think that it could have enough mass to explain these effects on cosmological scales. But what I was doing with my project was using these teeny tiny little particles. These are like 10 billionth the mass of an electron to simulate how dark matter behaves on a galactic scale. And the reason why this particular theory is super promising is because when it's been applied to stuff that we know a lot about, like the Milky Way, it's been able to come much closer than other theories at simulating the amount of dwarf galaxies that we see around it. So other theories are approaching around 300 or on the order of hundreds of dwarf galaxy-sized subhalos that are large enough to host a dwarf galaxy, as opposed to ultralight dark matter, which comes very close, or within, I think, 2 subhalos of simulating the correct number of dwarf galaxies within the Milky Way. And then another thing that's intrinsic to the type of particle is that these tiny little particles that are 1/10 billionth the mass of an electron cluster over space to form these waves that that we can simulate to kind of explain halo behavior. These waves bear a greater resemblance to what we expect dark matter to look like than most other theories of dark matter, which show a cuspy distribution. What a cusp is it's a kind of angular or triangular shape that approaches infinity at the center. And infinite densities are probably not good for physics in general. And we know that galaxies don't have infinite density at their cores. They approach some finite density as shown in red here. And so the core profile, or the solitonic halo profile of ultralight simulations, is very realistic to what we actually see in space. And so that's why it's a really promising theory. And I used it to simulate 4 different instances where dark matter has played a super large role in how the universe has developed. But I can talk about that in a later talk. And thank you so much for having me. And if anybody wants to ask any questions, I'm open.
Yep. We do have a question here. This is from Off-Road, watching on YouTube.
You've got an echo, Scott.
I think it's gone now. Anyways, this is about NGC 1277, which is deficient. It's deemed to be deficient in dark matter. Is it do you think it's completely absent of dark matter, or what's your take on this galaxy, if you have any thoughts?
So I'm just looking that up now. It did come up in the literature review that I did for my project that there were some galaxies that were deficient in dark matter, but potentially there is an issue with galaxies forming in kind of the intergalactic void, so to speak, where there's like basically no dark matter. But I guess there might not be a way to explain that yet. undercurrent theories unless it was tossed out, so to speak, after the structure had initially formed. Like when smaller galaxies collide to form larger ones, you can, in essence, provide enough kinetic energy to throw it out of kind of what you would see as a region that's higher concentration in dark matter. But I don't know if that would necessarily explain the lack of dark matter in the galaxy itself, because I'm not sure how the dark matter would just go away, if that makes sense.
Right. Okay. I don't think there's any other questions here. There was lots of nice comments about your
You have an echo
presentation.
again.
Yeah. I think I'm getting echo from your
I'll turn on my mic.
Okay. There we go. Anyways, León, I hope that you come back on to Global Star Party maybe next week and finish up more about your talk on dark matter. So fantastic. Yeah. Great. Let me come back on here with you guys, and we will transition. Thanks again. Okay, and at this point, we are going to transition over to Martin Ratcliffe. Martin has made a name for himself in the planetarium world, but he also is a gifted writer. He writes currently for Astronomy magazine, I think for a column that he's done for many years. And so, Martin, why don't you come on with me and introduce yourself and kind of fill in the gaps, because I was literally getting to know you at Alcon.
Yes.
But once I met you, it's like, sometimes you just connect with someone and it's like, you feel like you've known them your whole life. So that was my
totally fun. It's like, how have I not known you forever?
Exactly. I've heard of you for many years, and it just so. Anyways, it's a great pleasure to finally get to meet you in person.
Well, for me too, Scott, and it was a great pleasure meeting everybody, Chuck as well at Alcon. It was such a great meeting. David, of course, well, both Davids.
Yes.
And by the way, David Levy, I have a little treat for you later on, so look out for that. Something we spoke about at Alcon. That'll come up in a few minutes. Yeah, I've written for a little while for Astronomy magazine, as Dave Eicher knows. It's actually when the 50th anniversary issue came out, I went, oh my goodness, I've done it for 27 years, which is more than half the life of the magazine. And I vividly remember being a little kid in England where I grew up, getting very excited when I could buy Astronomy magazine off the book stand, never imagining that I would be involved for more than half the life of the thing. So I'm very grateful for David for keeping me involved for so long. Yes, as Scott said, my main full-time job is in the planetarium world. I've been in the planetarium world since the mid-1980s, starting in the UK and then moving over to the US, where I'm now resident. And when we were talking about, dark matter and things like that, and by the way, León, that was simply an outstanding presentation. And so I thought, well, I'll just delete a couple of my slides because you did such a good job there. But I will just go ahead and talk to some of my slides and just mention a variety of things. Let's see if this is coming up. Okay, there we go. And I have so many things I could talk about. I teach part-time at a couple of universities just remotely, and one of them is in Wichita, Kansas, where I lived for 24 years. And I actually do an introductory cosmology class. And so I thought I'd start out with this chart that I use when I talk about dark matter, just to illustrate to students without any science background what we're talking about. And the basic idea there is, there's a lot of light in the world and in the universe, and it doesn't always exhibit where the true, mass of things are. And so this Christmas light tree illustration kind of does that fairly well, I think. But what I thought I'd do is just really talk about my amateur astronomy experience as well. I'm going to show you a couple of things from the planetarium world first, though, and then go into my other passion, which is astronomical photography. And so one of the things we could do in the planetarium world is I work for a company called Evans and Sutherland here in Salt Lake City, where I am now. And I get to play with cosmological data sets and stellar data sets and asteroids and whatnot. I program some of this stuff on the dome so that it's just distributed out to all of our theaters around the world. And this model, and I think I may have these in the opposite order, I'll use this one first. On the left, this is a full dome view of most of the galaxies within about 500 million light years of our own Milky Way. And the way I've displayed this is to place our Milky Way, plane of our Milky Way vertically, where you see that dotted line. And you'll also notice that that's where there's a paucity of galaxies because we can't see through not dark matter, but the dark dust in our own plane of our Milky Way galaxy. And so that blocks out galaxies from the distance. But the rest of the universe, in our local universe at any rate, out to about 500 million light years, is filled with galaxies and clusters of galaxies. And the way I've oriented this particular thing on the left is you'll probably see a band along here. And that's not a mistake. Our local group of galaxies is right here. The Virgo cluster is right here. And this is what Gerard de Vaucouleurs termed the supergalactic plane. It's kind of a local plane of galaxies that sit in our local universe. And I use this to explain a few things about the dynamics of how our Milky Way is moving. And you'll see a few large superclusters over here in red. You'll see a bunch over here. But as we move out, oops, I have to go back one, don't I? As we move out into the farther Milky Way, these yellow lines delineate the motions of distant galaxies and how they're being influenced away from the Hubble flow, the general overall expansion of the universe under the expansion law that we have that Hubble discovered back in the 1920s, away from that flow because of the gravitational pull of these supermassive clusters of galaxies. So this diagram on the right is supposed to illustrate we are somewhere in the middle down here. Over in this direction are a number of very large superclusters of galaxies. Over here is a little, I think you might be able to tell, is slightly more sparse. Maybe you can tell that. You can tell it in the dome when it's moving. And really in a, it's very hard to do this statically, but I didn't dare do it in real time using Zoom because it's very difficult. But what I've done is overlay a measurement from the cosmic microwave background Planck satellite, which instead of looking at the cosmic microwave background itself, what I'm looking at is the dipole image, which tells which direction our Milky Way is moving in the universe. And so it's like a background speed measure, if you like. And what you see is on the left-hand side, the sky is a little bit warmer, indicated by this dull red color, and it's a little bit cooler on this other side. And so what that means is that our Milky Way is moving away from this direction and is moving towards this direction, which is where the bulk of the mass in our local supercluster is sitting. And that's what Laniakea represents, is in fact our local supercluster. That's kind of just by way of a quick intro into some of that stuff I do in the planetarium world. But I'm going to skip and change topic completely now and talk about where I live. I live near Salt Lake City. This is a dark sky map. And you go, good grief, how can you see anything there? Well, I live in Stansbury Park on a street called Cambridge Way, which for a British guy is very nice. It actually sounds like a tube stop on the London Underground, even though it's in Utah. But I like it anyway. So, and so you'll notice maybe down in the middle, there's a mountain range here. This mountain range goes up to 9,500 feet or about 2,500 meters, immediately to my east, which is where Salt Lake City is. So I have this natural barrier of light blocking by a large bulk of mountains. And if I show you where I'm building my observatory, you'll see what I mean. This was about 3 months ago, running a cable out to an observatory. It's still in the same state, by the way. I haven't done anything during this hot summer, but I'm planning to put 3 telescopes in here. And you see the mountain range in the background, which is blocking, well, it partially blocks street lights from Salt Lake. So I end up in about a Bortle 4.5 kind of sky, which is really not too shabby. And I've now, we had some landscaping done, so we now have grass. And you can see I have this little pathway, which I realized when I was putting this talk together is very carefully planned so that in the middle of the night when I'm walking back to the house, I will trip myself over and fall into the grass somewhere along the way. Anyway, I'll try and avoid that. So onto some dark skies and astronomical photography, which I love, and I'm going to kind of touch poetically on dark skies or dark, not on dark matter per se, but just on things that are dark. This is a photo I took a few years ago when I visited Flagstaff, which I know Dave Eicher knows and loves very well. And it was before the AAVSO meeting a few years ago. I decided to take a weekend and spend it on the rim of this little canyon that some of you may know called the Grand Canyon. And it was in quarter phase moonlight. So I was able to experiment with some really nice photography. And I love doing this stuff. And I think part of it is, you know, all of us on this call and people who are listening, we just love the darkness of the night sky. And that's part of what the theme is about here. You know, how do you feel about being under the night sky? It's so relaxing. You just feel embedded in, you forget your daily or even nightly worries walking around in scenes like this. And I love being able to capture some of that in photography. And so that's what I was going to talk about for the last part of what I have here. Little bit of history. When I worked in Northern Ireland, I worked at the Armagh Planetarium, and at the Armagh Observatory, they have the 10-inch grub refractor that JLE Dreyer used to finish up the NGC catalog. And I just loved sitting at the end of the same telescope. And on October 6, 1985, I recovered Halley's Comet with that telescope. And of course, Dreyer was the last person to observe it with that telescope. So that still gives me tingles on the back of my neck.
Yeah, that's great.
Yeah, it's a really beautiful memory. And also I did drawings of comets. This is Comet Halley in 1986 when everybody was reporting that it was a bit of a dud. This was in 20 by 80 binoculars. It was stunning. And I also took a Schmidt camera down to Australia, where there really are dark skies in the middle of Australia. So this is me with a Schmidt camera, which I still own. And this is a photo of Halley's Comet over, I don't think it's over Ayers Rock, it was over another rock. But I know it's not a comet talk, but I have to show comets because I love comets. And this is a shot that showing Halley. It shows the Omega Centauri globular cluster, and over here is Centaurus A, a galaxy. I actually have a shot somewhere with a meteor as well, but I couldn't find it. So it's one of those magical moments. David Levy, this is the photo I talked about at Alcon. I mentioned to David that I was at a conference in Seattle and then flew down to Chabot Observatory in 2007. And the amateur astronomers outside were viewing Comet McNaught in daylight. And inside the building was Carolyn Shoemaker signing autographs along with a bunch of astronauts like Alexei Leonov and Wally Schirra and Walter Cunningham. And she was part of that group. I ran inside and I said, you must come outside and look at this comet in daylight. It will be just magnificent. So this is kind of a special moment that I captured. It was a very famous comet discoverer looking through binoculars at a comet. So my best to you, David. I wanted to show you that, and I'll send that over to you at some point. So Other things I've done in my planetarium travels is I get to travel to interesting places like Bloemfontein in South Africa. This is the dome of a magnificent old observatory that housed a 28-inch, I think it was. And they've recovered the telescope. It was found in an old fire engine shed, and they've refurbished the whole thing. The lens is in the University of Michigan. It was actually run by the University of Michigan. And it gave me opportunity to go out to Boyden Observatory. I do a whole talk on this stuff, but I'm going to cut this really short. One of the magnificent things at this observatory is the very first camera that took a color photo of Mars, which Earl Slipher did. You can see Earl Slipher's book on the left. This is the actual camera he used. He used the telescope that I just showed you. But not only that, and here's Harvard plates from that telescope of Mars. I went down to the observatory in 2018 to observe the perihelic opposition of Mars with a 13-inch Clark. Here's Mars on the right. I'm going to do this very quickly, folks, because there's lots and lots of things to show you. I love photographing the sky from the southern hemisphere. And this telescope was just magnificent. I took lots of selfies with me and the glow underneath a giant telescope. It's a very historical telescope. This is me looking over the refractor at Mars, which is one of the evocative moments I didn't want to forget. That's my camera attached to it, doing some video capture. And on the left is my video capture in 2018. On the right is the very first black and white image of Mars taken in 1888 with this telescope, same telescope. This is a Harvard College plate. So as I say, this is a whole talk in itself. I've done some planetary photography with my C14, which I'm hoping to reset up in that observatory I was showing you. And in 2020, the year of COVID, I really spent a lot of time trying to fine tune my practice. And I essentially went in July from this image on the left to August, a month later, having fine tuned my experience. And as I say, I do a talk on that at another time. It's a lot of fun. Speaking of shadow, speaking of dark things in the sky, this was the 2012 annular eclipse of the sun across Monument Valley, and some really unique, the sun went down the edge of this cliff mesa, which was really amazing. Also speaking of shadows and dark, other solar eclipses are my other passion in addition to general photography and eclipses. This was Chile 2019, and I'm really looking forward to next year. And then in the South Africa, these are the kind of views that you get. Some of you may not have seen the shape of an emu in the dark bands of the Milky Way. Here's the body of the emu, here's the long neck, and here's the head, which is the Coalsack and the Southern Cross, of course. There's the beak. So yes, it's a very famous view from Australia or South Africa if you just see that.
Yeah,
so
you
just
can't
looking at
unsee it once you see it.
I know, once you see it, it's
Yeah.
right. This is the SALT telescope, a photo I took when I had some access to that telescope. Oh, by the way, I should mention that this telescope here is the Radcliffe reflector, not the Ratcliffe, which I am. It's no relation, but you know, I'll take it when I get it. Just some general, photography of things that I love doing. And then there's doing your own shadow against the aurora, or in this case, and I know David will love this one, Comet Hale-Bopp over Factory Butte in southern Utah, which was over 25 years ago. And now I live here. Can you believe it? It's amazing how life can turn around. And I find, so just the last comment, this was a very evocative and emotional moment. Because when I took this picture, I walked out onto this mesa. We're in the middle of the desert, and this comet comes around every 5,000 or 6,000 years. And I thought, the last time this comet came around, this landscape looked the same. And so I could stand out there as a human on this planet and just gaze up at this visitor once every 5,000, 6,000 years, and just have that cosmic view of the heavens, which we all strive for. And this was a very magical moment. So I thought I'd end just with, my happy place, which is at the eye end of a giant refractor. And that's the end of what I have, Scott. So thanks again for inviting me. It's been really fun.
Fantastic. Martin, thank you so much for coming on. We hope that we can get you back onto Global Star Party again. So
Yeah, I'd love to. Yep.
Yeah, that's great. Okay.
I just wanted to say, Scotty, that I thought that Martin's lecture was fabulous. I really, truly enjoyed it. And did you know that I also have a mild interest in comets from time to time?
I have heard that from time to time. Yes, indeed. That's why I thought, yeah, I'm glad you liked it. That's truly appreciate that, David. Thanks.
Great. Okay. All right. So, God, just so many great speakers here on Global Star Party tonight. As there is almost every time we do a Global Star Party, it's fantastic. But I'm feeling a special energy from this one, so it's great. Molly Wakeling, who has been giving presentations to Global Star Party over many of our shows with her Astronomolly program, always gives us a nice dose of science with insight into how the universe works with her beautiful astrophotography. She kind of mixes the whole experience of the mind of a researcher and scientist with the heart of an amateur astronomer and a great astrophotographer. Molly, thanks for coming on Global Star Party again.
Thanks for having me back. I'm glad we're back up and running on Global Star Party.
Yes.
Yeah, let me share my screen. So I originally made this talk for last week, although I think, Scott, you missed my email saying I could come because I didn't notice I wasn't on the schedule until about an hour before the show started. So I'm like, I'll just come next week instead. So I'm going to take a brief break from dark matter and talk about the Bubble Nebula, which is a really cool nebula I've photographed a couple of times, and it's up right now. So I want to highlight it as something to image and to go see if you have a chance. So what is the Bubble Nebula? It is an emission nebula. It's the bubble is from a stellar wind of a massive hot star, which I'm going to go into more detail in later. And it's near a giant molecular cloud complex. That gives you some really cool other stuff in that area to see an image with the interaction of emission nebula and dark nebula, and how in space those things are interacting. And it's a really gorgeous view. So you can find it up between Cassiopeia and Cepheus. It's probably far too north for our southern observers, but it's a nice treat for northern observers for sure. Kind of about halfway between the two constellations there. Yeah, that's where that's located at. It's relatively bright, at least the bubble part is, with an apparent magnitude of approximately 10. It's 7,100 light years away and about 7 light years across, the actual bubble part, which I mean, when sometimes like when you think about, like, we talk about sizes of objects that we look at in space, and it's like, oh yeah, it's 100 light years across, it's a galaxy that's 100,000 light years across, so 7 just sounds really small. But if you think about how it's so much larger than our solar system, and in fact, like, if you have to go all the way to Alpha Centauri and most of the way back in order to cross the distance of this nebula. So these things are very large to have come from only one star. And it's about 15 by 8 arc minutes across from our perspective here. So it's not small. You can see it in a variety of telescopes, and discovered by William Herschel in 1787, which it still amazes me how much stuff was discovered by telescopes in the 1700s. Like, the instruments they had and we're still doing this was incredible. Yeah, so let's talk about that bubble. This is this picture here is the Hubble picture of it, a nice, sharp, colorful close-up view of it. So the central star is pretty incredible. it is actually the one that you think, the bright one here. And you can see it's not actually quite in the middle, which is interesting, and I'll talk about here. So the central star is 45 times the mass of our sun. So, and really a truly enormous star. And because of its enormous size, it's sort of live fast and die young when it comes to stars, and especially at these masses. So our sun, being actually a relatively small main sequence star, it's going to live for about 10 billion years. That's billion with a B. But these really massive stars, it's only 4 million years old, and it's already mostly fusing helium at this point. It's burned through a lot of its hydrogen, and it will likely go supernova in the next 10 to 20 million years. So it's going to wink out its existence in a pretty short period of time, astronomically speaking. It has a hot stellar wind. So think about the solar wind from the sun, this cloud of charged particles that is being accelerated by the sun's magnetic field. Every star has something like this, and this one is particularly hot and particularly fast, moving at 4 million miles per hour, just screaming out of the star. And it actually is powerful enough it scoops up the colder surrounding gas and dust, which makes the edge of the bubble there sort of like a snowplow. And the reason why it's sort of asymmetrical, where the star is not really in the center, but kind of toward the edge of it, it's sort of this blobby shape, is because, like I mentioned, it's in a molecular dust cloud, so it slams into the dense cold gas more so on one side than the other. So in that side being this side here, you can see some of this cloud up here, and there's a lot of gas and dust in between. So it's kind of slamming into dust here, which is making it move more slowly than the side over here. So it makes this really asymmetrical kind of blobby shape. And this being a Hubble picture, it's in the Hubble palette. So here, red is glowing sulfur gas, green is hydrogen gas, and blue is oxygen. In reality, hydrogen gas also glows red, but in order to differentiate it from the sulfur, the Hubble palette is to colorize that red to be green for hydrogen, so it's easier to see. And this being a high mass star, it's already fusing the heavier elements. There's quite a lot of oxygen in the bubble surrounding it. All right, so I like to show what these things look like in other wavelengths, because we see these pictures all the time in optical wavelengths mostly, but sometimes you can learn something about it from looking at it in other wavelengths. So in the radio wavelength here, probably what we're seeing here is the hydrogen alpha line, the Lyman line, the 21 centimeter one, being, because there is hydrogen here still from its earlier stages. The picture on the right is what it looks like in infrared at, this is where, let's see, red is 2.1 microns, green is 1.5 microns, and blue is 1.2 microns, so pretty near infrared. But yeah, still cool to look at in infrared too. You could see some of the edge of the bubble here. Getting up into the higher energies of light, usually taking pictures in UV or an X-ray is not the same as taking it as we do optically. So these tend to be not the highest quality, and especially if it's not really been studied scientifically, there might just be kind of these wide survey images of it. So we kind of have this fuzzy blob here. These two things here are reflections. You can see kind of the shape of the telescope here. Nicely collimated.
Yes.
Over here in X-ray, I didn't double check, but I think that this is probably that central star, because it's so massive. It's probably hot enough to put out some amount of X-ray light, but I didn't verify this, but this might be that star there. So yeah, if you want to observe or image the bubbles, some advice is it's up now. It's the good time of year when it's in the sky at a reasonable time of night is June to January, and it's circumpolar if you live north of 30 degrees north latitude, which is most of the United States. So you can technically see it year round, but when it's pretty low in the sky, it can be harder to observe for sure. I think I have seen it myself, but I don't remember what size of telescope I was looking through. I have to go back and check my notes, but from some other reports, you might be able to see it with averted vision under dark skies in as small as an 8 or a 10-inch telescope. With a much larger 16 or 18-inch-ish Dobsonian, you can see the nebula. Probably using an O3 filter or a nebula filter will help pull that out. And you can kind of see it's faintly elongated, and probably this brighter portion is usually the part that you see most easily on this side here. Photographically, it's got tons of hydrogen alpha in this area, and it's relatively bright photographically as a result, especially if you're using an astronomical camera that is more sensitive to the deep reds than your standard DSLR. But you can still image it with a DSLR. It's great as a wide field where you can see there's an open cluster nearby. There's all kinds of dark nebula, all kinds of just emission nebula background, but it also looks great zoomed in where you can pick up a lot of the detail going on there. So it's really an object for whatever telescope you have is the telescope you can image with. Whether that's a short refractor or a long focal length Schmidt-Cassegrain, it'll look great in all of them. You don't need a ton of exposure time. The image I had in the title slide, which I'll jump back here in a second, is only 19 5-minute exposures under Bortle, about 3.5, and that's wideband, so no narrowband filters there. And that's this picture here. So you get a really nice open cluster over here and a cutoff part of it, but there's some dark nebula here. There's more nebula here. And yeah, so this is yeah, you don't need a lot of exposure time on it. Let's see, jump back. And it's great wideband. It's great in duo narrowband with a color camera. It's great in either HOO or Hubble palette with a monochrome camera. Really, this is something, an object you can image with basically whatever equipment you have, which is always a great thing to go for. And here's my picture of it in Hubble palette, which I've been really enjoying being able to do. A little more zoomed out than the Hubble picture, but yeah, seeing all those same colors of gases is really fun. This is a 19-hour exposure taken with 2 monochrome cameras. I have my main ZWO 1600, and then I was testing QHY 533, which I loved, by the way, from my backyard here in Dayton, Ohio, which is about Bortle 7, so a lot of light pollution here.
Yeah.
That's the great thing about imaging in narrowband is you can cut through that light pollution and pick up a lot of that nice, beautiful background.
Incredible.
And yeah, that's what I got.
That's all you got. That's a lot. It's a lot. That's great. All right. So, Molly, thank you again. So give us a little insight as to what's going on with your studies at this time.
Yeah, so yeah, I'm set to defend in November by hook or by crook. So I still got a lot of work to do. I've had some trouble with some of my calibration data, and we're still got some code development going on, refining some algorithms. But yeah, so still deep in data analysis. I'm measuring the neutron inelastic scatter cross section of oxygen 16, which basically means we're shooting neutrons at a sapphire target, which has aluminum and oxygen in it, and measuring how often the neutron actually excites the oxygen, so puts it into an elevated state. And that state will emit a gamma ray, and we'll get the scattered neutron and detect both of those. And so we're trying to measure how often it excites those states, because if you think about like a nuclear reactor environment, we've got neutrons flying around. There's oxygen in the water and in all the structural materials, and you want to know if you're getting more high energy gammas, and if your neutrons are losing more energy than you think they are, because you don't have the data on how often this interaction happens. So this will go into a database, which will feed into simulations in the future on things like nuclear reactors.
Wow. Okay.
Well, I think I speak with everyone when we say good luck and go get them. We're all rooting for you.
Thank you.
Yes.
Yeah,
That's
we'll get
awesome.
there one way or another.
That's right. That's right. Well, wonderful. Thank you, Molly. Thank you again, and we'll see you next time. Thanks
Yeah,
a lot.
thank you, Scott.
Take care. All right. So our next speaker is Dr. Daniel Barth, who will give a alternative view of towards the subject of dark matter. And Daniel, from what I understand, this is well, I don't know if it's a popular theory or an unpopular one, or for what reasons it's unpopular, but this is a theory. Now it's an acronym, right? MOND. What does that stand for?
MOND is an acronym, and hi Scott, and thanks for inviting me back to GSP.
Thank you. Yeah.
Hi everybody, good to be back. I'm going to throw wrenches tonight. As an educator, somebody who has taught both science and science teachers, I'm always challenging people to think critically, and I'd like us all to take a step back and think about a couple of things tonight. I'm going to bring up my favorite science guy, who is Thomas Kuhn. And Thomas Kuhn basically tells us about how science works. He's a philosopher of science. And Thomas Kuhn says, in contrast to this idea that science is a steady stair-step of great ideas, one upon the other, Thomas Kuhn describes the progress of science more like a cage match. Thomas Kuhn says basically, yeah, lots of people propose theories, and then we all go after them with daggers drawn, and it's kind of a last man standing sort of a situation. Let's take a look at what we have with dark matter. We have an effect. Vera Rubin, brilliant, one of my astronomy heroes, discovered non-Keplerian rotation in galaxies. Galaxies don't rotate the way planetary systems do. Planetary systems, everything goes according to Kepler's laws of planetary motion and Newton's dynamics, and the planets move more slowly as you get farther away. Pluto's orbit is 248 years, ours is 1, and Pluto is 40 times farther away than we are, but the time to orbit gets longer and longer. Galaxies don't do that. The orbital speed maintains itself consistently from very near the center to very far out. And a lot of other scientists have built upon Professor Rubin's work during her lifetime and since, and we see that this data is real. Having an effect, theorists sharpen their pencils and run in and say, ooh, let's posit a cause. How does this work? I'm going to remind you of what Newton famously said, hypotheses non fingo. And yeah, it was kind of a swear word with him. He basically said, I don't posit any hypotheses. I'm not telling you what gravity is. I'm simply telling you how systems work under the influence of gravitation. And the results were so astounding, and the predictions matched observations so magnificently. Newton is widely hailed as one of the most brilliant minds in science in all of human history. And I'll fight you over that. I think Newton wears the crown. But let me remind you, it took about 350 years for somebody to come along and say, oh yeah, Newton's not quite right. Here's how it actually works. And of course, no one believed him at first. This was Albert Einstein. Albert did something astonishing. Not only did he make the first correction to Newton's theories, he posited a mechanism for gravitation, space-time, and space-time curvature. Well, the idea that we see an effect and we now posit a cause and we go looking for that object that causes this effect, this is an old tune, and we've danced to this before. Phlogiston, the planet Vulcan, the luminiferous ether. Remember the luminiferous ether? This is what light is supposed to travel in. And of course, everybody believed it. It was taught, it was written in books. People refined the theory. Here's how it works. Here's the tensile strength of it. Here's the stiffness. Here's all its physical properties. Just one problem, it didn't exist. The theory worked great, but the posited object wasn't there. Eventually, we came along, we got this lovely experiment from Michelson and Morley. They looked at the speed of light, and they said, if we're moving through the ether, it has to have an effect, and it didn't. The same thing with the planet Vulcan. Monsieur Leverrier, who was the head of the Paris Observatory, one of the most brilliant and accurate observers of all time, he found these remarkably tiny deviations of the orbit of Mercury. And he said, well, Newton is boss. He's right. And if it's right, then there has to be something causing this. If Newton's right, there must be a cause. I posit a planet close to the sun. I'm calling it Vulcan. We searched for that for 2 centuries. Actually, it wasn't the searching that failed to find Vulcan that convinced anybody that Vulcan didn't exist. What convinced everybody was Einstein's theory, which said, I can tell you how gravitation works and how it changes the orbit of Mercury. I can match the effect most perfectly with my theory. And then finally, it was the astronomer Royal Eddington who went and looked, if Einstein's right, there should be a deviation in the image of a star. If that star is close to the limb of the sun, famous eclipse expeditions, and there's been much written about that. And what we found was, oh, this interesting cause we posited, this object, this thing, didn't exist. You go back to the great granddaddy of all of these things, heliocentric system, geocentric system. The 2 theories existed in tandem for more than 2 millennia. How? Why? Well, the reason was no one could come up with an experiment that would definitively show that one theory was not possible where the other must be. This was, of course, Galileo's invention of the modern astronomical telescope, his observation of the phases of Venus. And he said, look, the phases of Venus show us conclusively that the heliocentric model not only must be true, but that the geocentric model cannot be true. We have 2 theories, and there are more, but these are the 2 leading contenders. We have dark matter and we have MOND. And it's Mordecai Milgram, Professor Milgram from Israel, who posited MOND. And again, we're like Schrodinger's cat right now. We're in this dual state. And certainly one of these theories is vastly more popular than the other. Oh, no one really likes MOND. Nature doesn't care, friends. Nature is under no obligation to perform according to your mathematical theories and dictates, none whatsoever. We, on the other hand, have an obligation to adjust our theories to fit the facts. And the problem is, right now, there is no definitive experiment that says, Eureka, I have found it. Here's what dark matter is. And we can detect it where it needs to be in order to be causing this effect that we see. Interestingly, just yesterday, an article came across my feed. Some scientists were studying the Hyades cluster. And they said, you know what? The expansion of the Hyades cluster would make a lot more sense if there are small black holes in the Hyades. Well, in fact, they said, oh, this is a lovely theory. And if it's true, then it's a nail in the eye for MOND. And then they went on to say, oh, but the problem is we haven't been able to detect any black holes in the Hyades cluster. So our theory says black holes would make it work very nicely. And if that's true, then MOND doesn't work very well, and maybe we can throw it away. Oh, but by the way, we haven't been able to find the cause we're positing. Right now, friends, we are in this lovely, golden, magical era where we have 2 powerful, amazing theories, and we have people going out, and it's very clear which theory the astrophysical and astronomical community favors. It's very clear. And there's, you know what? Science isn't about popularity. If you would ask Galileo in 1610, how many people do you know who agree with Copernicus and the heliocentric system? The number would have been vanishingly small. In fact, the great overwhelming majority of the scientific community, virtually everyone in the scientific community, really believed that Copernicus was a nut. Galileo was kind of positing this idea. It couldn't possibly be true. We've known for centuries, for millennia, that the Earth is fixed and at the center. All of our science is based on this idea. We have all these observations. We have this wonderful theory. We have the geocentric theory with all these lovely tuning and adjustments, and we got it just about just right. There's just a few little things. It's through these cracks that new science emerges. We have to be humble before the facts. If we're choosing favorites among our theories, then we're engaging in, well, let's just call it less than purely scientific behavior. We get data first, and we modify our theories to fit that. The idea of what dark matter is and where we can find it, we've been shrinking the box. Oh, we've got a better idea of where to look for it, how much it weighs, how it interacts. We're looking, and we've got a smaller and smaller box to look for that mouse. But as yet, we've seen no mouse. No one's detected a dark matter particle. No one can tell you what a dark matter particle is. They can simply tell you, I have this marvelous theory, and if there are dark matter particles, they're performing this function, and they're basically positing a cause for a gravitational effect. But we haven't seen the cause yet. Do I have a favorite amongst these theories? Yes, I do. That doesn't make any difference, and I'm not going to tell you. My personal favorite or my ideas influence nature's behavior not one bit. So we've got all these wonderful scientists, and my goodness, I am so impressed with all our speakers tonight and their research and their scholarship and their precision and the way they handle data. But I'll remind you, all of these scientists are working to perfect and basically get a solid grip on a theory that works. If you were to be like Newton, you would say, I have a theory that works, but hypothesis non-fingo. Let other people go out and explain what the cause is. I'm simply going to tell you how it works. And the Lambda CDM community has done a spectacular job of giving us a theory that shows how it works. We still need our Einstein. We still need our Galileo. We need a genius to come and develop an experiment and show us definitively. And at some point, I'm sure this will happen. Somebody will come up with a technology and an experiment and basically kill one of these theories, put the last nail in it, and it's dead for good because I've proven this theory cannot be true. I'll remind you that Galileo's confirmation of the heliocentric system didn't work because he proved the sun must be in the center. His work basically championed the heliocentric theory because he proved the geocentric system cannot be true. This is exactly what Thomas Kuhn says. We have theories in the scientific workspace, if you will, and people are going at it hammer and tongs because it's a very rare thing to posit a theory that becomes textbook. It's much easier to advance your scientific career by shooting down somebody else's. That is by far the more common scientific activity. And, we're moving forward. We're gathering data. But I want to remind everybody that a good theory is not evidence of an object of cause. We still haven't detected it yet. I have confidence that we will. I have confidence that either one of these two theories will be sorted out, or it may be like the string theory, where we had 5 different string theories. And then someone came along and said, wow, look at this. Mathematically, they're all the same thing. It's just which side of the die are you looking at? So we have a lot of work to do, and we must keep Occam's razor sharp. We must hone our skepticism. We must remember the difference between talking about theory and detection of objects and the confirmation of a cause. We're still working on it. It's still a work in progress. And I, for one, am not willing to say, 98% of scientists believe, and therefore I do too. Science isn't about polls, and science isn't about belief. Science is about data. Let's go get some. There you go, everybody.
Awesome. Okay. So, well, I think
I
that,
just needed to interrupt for a second, Scotty, if you don't mind.
sure.
That
Absolutely.
was thrilling. I mean, I really hope someday you'll tell me what your pet theory is, but I totally found it. It was a breath of fresh air. And I think that I could imagine Clyde Tombaugh sitting next to me, laughing and doing his puns and saying, you know, you have to look at the big picture. You have to look at what science really is. And we don't know. We don't know most of what we need to know about the universe. One day we will, but not for a very long time. Congratulations, Stan. That was beautiful.
Thank you, David. I'm humbled and very pleased. Thank you.
All right.
Would you be able to, I think a lot of the audience doesn't know what MOND is.
Oh, all right.
Describe it.
MOND stands for Modified Newtonian Dynamics. It was proposed by an astrophysicist named Mordecai Milgram, who works out of Israel. And Professor Milgram said, I don't like the idea of positing this lovely effect because of a particle we cannot see and cannot detect. He believes that what is happening, in fact, is that basic Newtonian dynamics needs a minor modification that will show that normal gravitational function produces all these results where small systems orbit in a Keplerian manner and very large massive systems do not. MOND, some varieties of MOND also posit that some constants of nature may change over time. Again, that's a purely hypothetical posit. We have no data to support or reject this idea. We certainly haven't been observing and recording constants of nature long enough and with great enough precision to make any kind of a reasonable stab at that. However, Dr. Milgram's theory does explain, and as the cold dark lambda cold dark matter theory does, it does explain the behavior of non-Keplerian rotation of galaxies and other effects. And there have not been a great number of people who said, ooh, that's interesting, let's test it. A few have, but there's not been a great surge of interest in testing Dr. Milgram's theory. He won't be alone if he passes and no one confirms his theory during his lifetime. I will remind you, we lost Dr. Gilbert Levy just about a year ago, the man who built and was the principal investigator on the labeled release experiment on Viking. And he claims to his dying day to have discovered bacterial life on Mars. And the scientific community goes, they don't believe him, but in fact, to confirm or reject Professor Levine's theory, we're going to either need a very robust sample return, which we're working on, or my favorite, boots on the ground on Mars. It would take an astronaut scientist an hour to dig up some soil and run some tests and find whether or not we had any sort of bacteria or active DNA or anything in the soil of Mars. That would be definitive. We haven't done that test. Dr. Levine, I don't know, maybe he deserved a Nobel for finding life on Mars, but you know what? He had the same problem lambda cold dark matter community does, the same problem MOND does. No one has done the experiment to confirm or kill his theory. It hasn't been done yet. And science sometimes takes time, and sometimes more time than we've got. But we have faith in the process that's worked for millennia, that science will proceed. We add to it as we can while we're here. And I don't know, I hope we have a grandstand seat after we're gone to see how things turn out. But either way, the process will resolve this dilemma. The scientific process is ultimately self-correcting. And if MOND is a bad idea, MOND will die. And it wouldn't, if MOND turns out to be the thing, oh, you didn't need this thing. All you needed was to more completely understand gravitation. That would certainly be a much more common event than, oh, I've discovered an entirely new type of particles and things that cause great impact on galactic size and intergalactic size structures. We've frankly done the let's modify gravity thing successfully more often. So does that mean we will again? No. And MOND is really interesting. MOND, all capitals, and Mordecai Milgram. And Mordecai is not spelled quite the way you think, but I'm sure if you type him into your search engine, you'll find him. And it's worth looking at. It's always worth exploring the other fellow's theory. If nothing else, it gives us an idea where to look for the next piece of data. A theory we want to shoot down points us where to look, sharpens our perception, makes us focus on new instruments and new experiments. Kuhn was right. It's a cage match. Let's put on the gloves, lock the door. Let's go. I'm ready.
I think also what really sold me on your lecture was the appearance of your colleague, the big black dog that came by in the middle of your lecture. That dog has all the answers.
All right. Well, thank you very much, everyone. We are running behind at this point and need to transition. Our next speaker is Maxi Falieres in Argentina. Maxi, thank you for waiting there patiently, and you have the spotlight here.
Well, thank you, Scott. Good night, everyone. How's it going? I didn't see you for a long time. Molly, Adrian, well, Cesar, León, a pleasure to meet you. Well, Daniel, of course, your speech is impressive. Even in Spanish, I could follow you when you speak, but I think I understand pretty much. So, well, what I'm going to show you for tonight is basically what I've been doing last week, almost. Let me share my screen. Okay, do you see it?
Yes.
Great. So, like I showed you in the last GSP, I bought this Dobsonian reflector telescope because my goal for now is, well, when I do astrophotography, I want to and give I want to do visual observations I'm doing astrophotography too, so I need something portable, comfort, and when you put your eye and that's it, and enjoy the skies. So, well, I bought this particularly Dobsonian in a good price in second hand, but anyway, I also searched for almost this one because it has a really long focal length, so allows me to observe planets for Saturn, Jupiter, and also the moon. So, well, I watched it through the telescope, and when I saw Saturn, even my wife said, "Oh man, look those rings." So if she is impressive, so I'm glad to know that. So basically, I've been doing some observations, but I had an idea, so I made this. I put the Dobsonian telescope above the mount, equatorial mount. Well, for Nico and Cesar, this is sacrilege because it's not a Dobsonian, but I give it a try to capture the moon and the planets. I also like to do planetary pictures. So I went to try it, but also tried to do some deep sky objects first because Saturn was very low, and the skies aren't the good ones. But anyway, in this case, this is a capture of my view of the Bug Nebula that I took with this scope and my ZWO. And this is only 1 minute capture, and I give it a try. It doesn't the same that the f4 maybe. It doesn't have the lens correction and everything, but I really like to do this. And then when the Saturn start to comes up more above 40 degrees, maybe. I've been capturing practically this, but this is unsharp. When I get through this Registax software, this is a pretty one, but pretty old, but it works really good. When you open it, let me put more zoom it. When you only go there, you can see it start to get more detailed. And when you do the RGB balance, it goes to that colors. So I run maybe 8 or 9 videos of that night. I stack everyone and then they rotated everyone, so I could have this. This bar is bother me. Okay. This is an example of what I get processing this with the 8 inches f6 telescope. And I did this, rotate this because change you the perspective of why you see it, maybe in the north hemisphere you can see like this, but here you will see this because this is the south, so it's here is up and the north is down, for example, but it's all perspective, that's all. And also what I've been doing was trying to capture the moon, but I didn't change the lens or with the same camera and everything. So basically, when I run this, this is a stack image, but when I start to process this, I get this. So the details that I get, it's this is what I wanted a long time ago. These are the details that I wanted. The shapes of the craters, the center of that craters, and the small ones. The condition of it wasn't really good for planetary because the scene was terrible. The jet streams above in the high winds. Now it's in no that they were really bad. So this is another place. I don't remember the name of this crater, but when I process this, I get this. So now even for that bad night, I could get all these details in the moon. So I'm really happy to do this. This is that night with the gear outside, and Well, you can see here's the camera, the Barlow lens, here's the guiding camera, and here's the Astronomy Plus commanding everything. So, and here's the notebook connected only to the
Wow,
main
nice
camera.
setup.
Yeah, maybe if my neighbors was this, they think that I'm going to put down some airplane or something, but you know.
Yes.
Anyway, I didn't bother about the lights and everything because I was doing planetary and I don't need a dark place. But anyway, ran almost 2 a.m. It was freezing. I was tired. I had to work the another day, so I tried to process everything, all this in the weekend. But well, in the last GSP, we had a full moon and the super moon that everyone calls. So I give it a try only with the Nikon camera and this Dobsonian. So I put it outside when I finished my talk, and I was trying to focus, capture, and everything. So I get this full moon of that night of the last GSP. So I'm really happy to do this because it was, I don't know, 10 minutes only. I put this outside, put the camera, focus, and that's all. But anyway, it doesn't the same if you are doing deep sky objects. It depends on what you're going to do. The tools are changing. You have to change. So well, that's it for tonight. Thank you for watching, and
Thank
well,
you.
Cesar, I say you hello and vamos River Plate. It's playing now River Plate, so it's my favorite football team.
Great. Thank you so much. Thank you,
No,
Maxi.
thanks to
Yeah,
you.
great to see your wonderful work, and
Thank
we'll
you.
see you next time. Okay.
Okay.
All right. Okay, so now we're moving from Argentina to Brazil with Marcello Souza, who is the editor of Skies Up magazine, but that's the least of what he does. He is a tour de force of astronomy education in South America, and he runs one of the most successful programs with students and is really making big changes in his country. Marcello, thank you for coming on to Global Star Party.
Hi, nice to meet you, all of you. Thank you very much for the invitation, Scott. It's a great pleasure to be here.
Thank you.
I will share now my screen in a moment. Let me show here in a moment. Oh, yes, it's working. I will talk also about the dark matter. Also, I will talk about dark matter.
Okay.
I have a different idea about the MOND. First, I will we organize an event 1,000 meters high here inside the Dark Sky Park. That's the first Dark Sky Park in Latin America. We have 26 people that participate in this event. It was the biggest event in a dark sky, inside the Dark Sky Park. Here in Brazil, the first one of Latin America, and until now we have only this one in Latin America. Here you can see the group that was there, and it was a great experience because you have the opportunity to see 4 planets, to see the region near the Southern Cross, Scorpius, Sagittarius, and show to this audience information about astronomy. And it was in a this is the place that you have a dinner after the event to celebrate the event. It was very cold for us here. It was very cold. It's almost 14 degrees. For us, it's almost snowing. And here was the image that I took with my smartphone in the moments that a meteor cross is near the Southern Cross here. I don't know if you can see here the Southern Cross, and here you see a meteor here near the Southern Cross. I didn't see the meteor because I was taking the picture, but I saw later. And now we begin to develop activities in 10 cities here near us. And what we did, we find places in each city that you have a dark sky. And now we organize an active visits to all of these places. We have now nucleus of our astronomy club in all these cities. Then they are organizing many activities there. Then soon we'll have a new image about different places here. And this is something new that was announced yesterday, that will change our idea about from where that came the water from the planets. The research is analyzing the samples that Hayabusa mission took from the asteroid Itokawa, and they found that they have evidence of past fluid activity on asteroid Itokawa. Then it is possible that the water also came from asteroids, not only from comets. This is a new results that was published, I think, is few days ago. I read it yesterday. I was announced to the press yesterday. It's something fantastic that will change our ideas about from where that came the water. And this is something that happened on May 19th, if I'm not wrong, is in the M101, the Pinwheel Galaxy. And the Japanese Koichi Itagaki, he saw for the first time a supernova here in this galaxy. This was in May 19th of this year, and I tried to find this supernova today. I will show a picture that I took today using the telescopes of from the Las Cumbres Observatory. And here is the image. This is where is located the supernova. This is not my image. This is where is located the supernova. And here you can see an image before and after the supernova. Here is the region that we can see the supernova. Here is the supernova. And this is the image that I took today. I think I'm checking yet, but I will show here from the Falks Telescope project that here I have another, the supernova is still here. You can see the supernova here. I'm checking, but we have May, we are in August, June, July, 3 months. That the supernova is very bright yet in the constellation. But I'm checking, here is the position. Why I'm talking about this galaxy? This is the reason that I'm talking about this galaxy. This is a video, I don't know if this video is working, about the rotation of the galaxy. Let me change here. I did something wrong here. This is, yeah, I lost everything here. The rotation of the galaxy. And when we talk about dark matter, what we are why we're using this kind, looking for this kind of matter, is because in the theories that you have, as Daniel said, we don't have an explanation about what is happening with the rotation of the galaxy, because it's different from what we imagine that happens. because if you use the laws, the Kepler's law, we imagine that when you go to the borders of the galaxy, the velocity of the rotation will be low than if you compare with the regions near the center of the galaxy. These are the Kepler laws of planetary motion that we use for the planets of the solar system, and we imagine that this will work also for our galaxy. And this is something that is you can arrive in this using the gravity law of gravity from Newton's gravity law. And here is what you see. This is from Wikipedia, from graphic from Mario de León. Here is what we make the observations of. Specifically, this is from one galaxy, and this is what was predicted. You see that it's very different, the results. And until now, we don't have an explanation for this. To explain this, what we imagine that something different is happening in the borders of the galaxy, and this can be explained if we find matter in this region that we can't see. This is the reason that we call dark matter. And if you have this kind of matter around the galaxy, this can affect the movement of the borders, the part of the galaxy in the border of the galaxy, and this can explain this. But until now, we didn't find. Then we have the theory that Daniel said, the MOND, that they made a modification in the laws, Newton's laws of gravity. They don't have now in the border of the galaxy, they don't consider that you have a duration is r square. They use another kind, a third, something like this, but only in the border of the galaxy. This is something that you don't have a complete theory for this. It's something that you made change in the classical theory to adapt for the problem that you have. This is the reason that many people, and I including these people, think that something that is only adjustments and using the classical theory, and there is a region that have strong gravitational fields. Then I think that, and we have the correction made by Einstein with the his theory of gravity. We have a different kind of consideration about the gravity. It's not a force, then something different. And then, but he works with the classical theory, changes the classical theory. I think that both are not probably we will find a different explanation for what is happening. I think so, because dark matter is something that also we don't have in theory, something that we include because we don't have an explanation for what we see. Then it's something that open. This is the reason that we have a job for a long time as astronomer, because I need to find a solution for this problem, like the problem of the expansion of the universe that is faster than we imagine. Then the same way we imagine that we need to consider some kind of energy that is doing this, but something that you don't know what is. Then our view of the universe today, most of the energy of the universe that you consider the matter of the universe, we don't know what is in the traditional theory. I worked with the solution of the Einstein equation. This is in the left part here, you have the traditional prediction, and in the right is what is measured. You see that it is not the simulation to show that it's not slow. It's not slower the velocity in the border of the galaxy. A difference that we were predicted. According to the Kepler's law, it is associated with conservation of the angular momentum. Then we need to change all the theory that you know, the physics that you know, and then you have two options. We find the dark matter and continue using the classical theory that you know, and we propose something that we change everything that you know. We need to have produce a new theory to explain what's happening. Then I have two solutions. I don't know what will happen in the future, but I think that we didn't find yet a good way to explain what's happening with the galaxy, in my opinion. Then this is an image that they use to show that probably this gravitational lens effect was caused by the dark matter. Then they use this probably to justify the theory of the dark matter. But until now, we don't have a candidate for the dark matter. This is a distribution, composition of the universe today that we imagine. Then 70% of the energy of the universe is from the dark energy that is associated with the expansion of the universe that's faster than we imagine. 25%, almost 25%, will be caused by the dark matter that you don't know what is. Then almost 95% is not associated with matter that you know. Then these are the theories that we consider nowadays. Then we have many things to find, and we need to find an explanation for this. And then finish with the image of Skies Up, the magazine, the new edition. That is a fantastic magazine. Thank you very much for the attention. I think that's something that we need to talk, man, it's something important to discuss, because we have many mysteries that we didn't find yet solution. Yeah.
Agreed. Agreed.
Thank you very much for attention.
I posted a link to the article in Nature about asteroid Itokawa and the water and organic matter that they found. They're finding on that asteroid, and yeah, it's very compelling that to have asteroids maybe join comets, and the idea that of life being brought here to Earth from bombardment of those two really different kinds of objects. So
something new, no? That we didn't imagine, ever consider that our water comes from comets. Now we have also asteroids that can bring water. That's something. When the technology and the new equipment that we have is helping us to build new theories, and they also have new challenges that to explain what we are measuring. And this is the way that science, the evolution of the science. And we have I don't know if that's paradigm in English also, is this that you say? A paradigm in Portuguese is something that we consider as something real, this like but we need to bring, if you have new information, new data, you need to build another theory to explain this, and this is the way that the science happens, the evolution of science. And with these new data, we need to find new models, and then we are going to have an evolution. Thank you very much for the attention.
Thanks very much. Thank you. Okay. Up next is Cesar Brollo. We will jump back down to Argentina. And Cesar, are you with us here? You've been waiting very patiently. Thank you.
Hi, Scott. It's a pleasure enjoy tonight with the audience. Here is my telescope. Now I am making the same that the last week, but without a lot of clouds. as we have in
it's
the
clear.
last edition. And as tonight we starting talk about, we talk about maybe somebody is okay. Thank you, Marcello. How are you? Okay. The idea is that show in the last week that I couldn't, Omega Centauri, and Omega Centauri have something of the idea of a huge power of gravity effects over this cluster, the biggest cluster in that we can see in the south hemisphere. And here I can show you live image of the cluster without clouds tonight.
Yes.
I have clouds, but the idea is show something that is how many times I told about this cluster, about the singularity to be the center, the core of the whole galaxy that was absorbed, was taken from the Milky Way, disappear completely. The arms actually is part of our galaxy, and you know, the capacity of the huge forces of gravity. Of course, that here we can talk about dark matter, but maybe because we can't, feel, and this scientific feeling about instruments, some deviation of the light, but two Chilean astronomers work over this cluster, and they found, or they think, that it's very probably that the cluster have two black holes inside. You know that huge forces of gravity are compelling and are very connected with the all ideas of dark energy. Actually, we know with the big forces of gravity where is, or much better say, we can see how this matter is not matter, is, I don't know. We are talking about the same. What is this? I don't know. And but when we have the huge forces, really we are searching. Sorry that I was unable to stop the guiding, because I don't need guidance now, and much better without guiding.
Yeah.
Maybe I can show
Got
you
a nice
in a
focus.
single. Yes, the focus
Nicely
is
focused.
great.
Yeah.
It's maybe, you know, that is a live image. It's not, but the size of the cluster is amazing. Maybe we can get, and let me see if I can give you a picture without movement. Yes, maybe less. I can try now. Okay, we can put less time, a little more of gain. we can try. If I can give you a zoom image of the cluster with a little more of gain. Here, much better. You can see the huge amount of stars. This cluster have more than 1 million stars, and to maybe at least two. Here is much better. Two black holes inside. It's a very interesting cluster to study. It's an example of forces of gravity, and it's very interesting to understand how work inside the cluster, the forces of gravity. It's really something connected with all that we was talking about. And it's something magic that we can show in a live image, something so far away and so magic, where you can see millions of suns in a big ball. It's incredible, really. Sometimes we lost the idea of the time that we live. So we saw possibilities with a small telescope and a camera, sensitive camera, and really you can see this small telescope and the sky, and you have two scales: the human scale and the size of a telescope image. That is incredible, the sensitivity and the possibilities to have this kind of image.
To do it live from your balcony under included skies.
Yes, this is not it's not a wallpaper. It's not the wallpaper. It's the it's the sky. Cool. Yes, cool. Yes, you can see in the screen. Enjoy the incredible of the cosmos. It's amazing. It's something that we never miss the capacity of how do you say, of to be amazed. This is something that like a kid, like a child, you know.
Yes.
Thank you, Scott. This was the live image for tonight.
Thank you.
Omega Centauri for everyone.
Thank you. It's a nice gift. Nice gift to have a live image like that from the Southern Hemisphere. It's also interesting to mention, I would like to know more about the discovery of it, but Edmund Halley was the guy who's credited of discovering Omega Centauri back in 1677. So it's a real pleasure. I have seen this object on a number of occasions from the Southern California deserts, and it is absolutely stunning to observe. So
yes.
But anyways, thanks again.
Thank you, Scott.
Cesar, and we will see you next time on Global Star Party. Take care.
Absolutely. With a new option.
All right.
All right.
Okay. All right. And up next is Adrian Bradley, who's been waiting patiently to show us his latest night sky photography. Adrian has shown, to all of us on Global Star Party, his progressively better images of the night sky, also his knowledge of what's in the in his objects. He's taking wide field shots, but he's been able to pick out all these very interesting objects in his images, and he's made nice long trips to find those dark skies, not only in the UP where he lives, but out here in the Okie-Tex. And I know that he hopes to travel to many other places to find those dark skies and those beautiful landscapes. So I'm going to turn this over
Yes.
to you, Adrian. Thank you very much for coming up to Global Star
Yep.
Party.
Thank you for having me, as always. I tried to plan what I was going to start off with because the theme, of course, is staring into the dark. And I do that all the time when I go out to these places. The only thing you see is darkness. And then as your eyes dark adapt, you begin to see what you're trying to shoot at. You see lights from distant towns, light pollution from distant towns, different times of the year that you shoot. And coming from photography, but wanting to have more of a scientific standpoint, you mentioned, Scott, images started getting better and better. Well, there was a noticeable time when that seemed to happen. And that's when I stopped trying to take beautiful image and steal from the night sky to create a portfolio and do it the way that many of you who may do photography for a living, or you'll post something online and it'll be the Milky Way in front of something, some beautiful foreground. And there's some great images out there, and I will be sharing some of mine. But I wrote some notes based on the themes of all of the talks, and Dr. Daniel Barth in particular, looking at you and you maybe soon to be doctor in a few years, León García, with not so much conflicting views. If we were to post these things, we're on social media, but we may be posting these things as conflicting views, and I think that's a wrong way to look at it. We're posting them as opposing views.
Right.
We have so many people who, Ohio State versus Michigan sports, and they want their team to win. And I think some of this sports thinking comes into science, and it's hard to, especially in an American world, we want to win. So we want our photos. I'm going to start sharing my screen if I can. I thought I could. Oh, there we go. My screen. Okay. So, great images start out kind of like this. Focus, not so much. You're staring into the dark. And then you finally take a long enough exposure and you've got these bright discs. We're in a world today where someone would, take these discs and say, hey, I got stars, I'm done, I'm going to post this and, be happy with it. And they don't realize that there's something else here. And then they'll take this photo and say, oh, we're close, and they'll go from there. There's a lot more here, which I'll be showing in the Lightroom screen a little later as to where I finally ended up. But you have to believe, and I know humility is a big part of it. I wrote a note that my images started to get a little bit better once I started taking images with the idea in mind that I'm collecting data out here. I'm showing people what I'm seeing, and not so much trying to take a great image so that I can post it online and get the accolades. As a species, I think some of the questions we're trying to answer about dark matter need to be answered by admitting that we're probably not going to be there to see the final answer, at least on Earth. This is all stuff you mentioned, Dr. Daniel Barth, but it gets through. And even León, continuing your work in dark matter, now your challenge is to continue to study, as it's very active field in dark matter is still going on, dark energy as well. And I'm sure someone is trying to figure out how to tie the two together. Understanding our universe is a common thing. And sometimes in the photography world, we get caught up in wanting our best pictures to step forward and sell our pictures. I happen to sell this image of Cygnus, and I'm going to get into part of my discovery tonight. I'm going to talk about other regions of the Milky Way that you can shoot. Our own Milky Way, is it dark matter, or can MOND, and I believe that theory MOND, that does explain movement in our galaxy. The large galactic clusters is where I thought there was a little bit of trouble with MOND, and Dr. Barth, you can correct me if that's your understanding, or if there's more to it than the simplistic common photographer that I am trying to explain it. We had one of our astronomy clubs did have a talk. And speaking of astronomy clubs, I'm going to segue my own. In Michigan, there is a star party called Astronomy at the Beach. I should go ahead and mention that if you're watching this and you're from Southeast Michigan, September 22nd and 23rd, that weekend, that Friday and Saturday, we're going to be at Island Lake Recreation, or Island Lake State Park. So quick little plug for Astronomy at the Beach. As we get closer, Scott, I'll send you some messages about it and have a little more of a presentation for that.
Great.
But yeah, but let's get back to some of the images. Milky Way photography in particular becomes a little more about these panoramas, and you got this galactic core, bright. There's this other region here that I'm going to talk about from the standpoint of capturing all of the data that's in here. You have the North American, the Pelican. This is Deneb, I believe, and Satyr is the star here. And there's so much stuff here that is often imaged by deep sky imagers. Will come into this region to image. You've got this rift here, and this is Lake Huron. So we're looking across Port Huron in Michigan. We're looking across at Windsor, Canada over here. This tends to be a popular target, and I take images of that popular target all the time. In this case, you had a campfire. So you had people on this beach enjoying the Milky Way. I did another panorama. These are images that many are going to look at and say, this is a beautiful image. It's the summer. And when we're not being smoked out, we, by wildfires, we really dig in, and we get what data we can. And the more resolved, whatever we do to get resolution, it makes our overall picture stand out even more so. But my challenge now is to make this sharper. I had the lens that I used did a great job of revealing some nebula here, cat's paw, lobster claw. There's these artifacts here, but then you've also got some detail in Ptolemy's cluster and the butterfly, some detail that a simple image doesn't get. So when taking photos, I decided I wanted to do more than just take a stock photo of the Milky Way like you see here. I want details to be present. So that's when I decided that's, with my photography, that's what I would focus on. And sometimes the part of the Milky Way is not out, and I don't want to stop shooting just because I don't see the galactic core. Cygnus in the northern hemisphere is up more months of the year than the galactic center. So experiments in trying to capture Cygnus where it's dark enough, you get all of these dust lanes, you get all this detail. But what if it's not dark enough, such as this finished picture of what I was showing earlier? To get from here to a finished image, it takes some processing and it takes multiple shots. Once you get the, like, I liked this and I knew Cygnus was here. This is a very bright rural area. Maybe Bortle 5, if I use my meter. I take my sky meters out because I not only take images, I hit the sky meter to see what is my darkness level. So when I do different images, different times, different apertures, it gives me an idea of what it is I can get. With a slightly more aperture, f4, my foregrounds come out pretty good. But with wider aperture, you can start seeing these regions in Cygnus as they begin to set. And my lofty goal was to see if I could show this part of the Milky Way in this very bright area, not so dark area, could I still pull off getting that region of Cygnus? And the image started like this out of a modified camera and ended up with the processing that I've done. So all of it is an iterative process. You don't just walk out and go shoot Cygnus. This was an experiment in getting Cygnus with a bright moon. This was a 3/4 moon, which will show you, this is the moon that I attempted to capture Cygnus in. There's the North American Nebula again. Shows you how bright this region is. Now, of course, I'm using a modified camera. Those of you who are using cameras that don't have the hydrogen alpha filter pulled out might not get this in such detail, and might not, any of the other, even this little speck here, nebulosity, and this is Cesar. There's nebulosity all around here. With clouds advancing, and I ended up near a tree and had pretty good tracking, so I just stayed here and I shot. These sort of shots may not win Pulitzer Prizes or may not be understood by anyone except a Milky Way enthusiast. They may look up and go, there's the Cygnus star cloud here, and there's the Cygnus rift. And I'm perfectly fine with that, because not every shot you take may present itself as the absolute most beautiful shot you'll ever take. When the moon is out, I don't want to stop shooting. And let's see, so focusing on what the moon can do, this is another discovery image. I shared it last week. I'll talk about how did I know there was a moon bow sitting over here, and quite possibly another one starting there. Well, going back to this bright 3/4 moon, I had no idea that a 3/4 moon this bright in this location could produce a moon bow. I saw some column of light, did not see the colors that you see here. Decided to take an image. That's why the stars are kind of oval here, but you see stars, you see these clouds, and the colors showed up, and it surprised me. And anytime you can surprise yourself with photography, that's when the magic happens. And that bringing a scientific mindset to photography keeps you from taking images that, I shared this image online, of course, parading the image around and saying, look at what I've got. Maybe I'm not in the position to do this, but Bray Falls is a very brilliant young astro imager who was called on to do the some of the astro imaging of an O3 region that was discovered next to Andromeda. The scientific process calls for more instruments when there's time to verify that what they have is indeed a true O3 region and figure out whether it's near Andromeda or is it an artifact in our own galaxy. And, you know, we've yet to see the scientific value of this region. It is an interesting discovery, but a working astrophotographer instantly beautifies the image, which we all process these images so that they represent a little more than the naked eye can see, but you know, still it's a believable image. And you package it up and you sell it to make money. It's, you know, making a living is a part of this. It's, if you're in the profession, you make a living with it.
Nothing wrong with that.
Nothing wrong with that at all. So,
Right.
you know, but you still hope that it's a, when you process things as a, you know, for the greater good of humanity, again, you get kind of out of the rat race of my images need to be like this, because the common man, common woman, especially in our country here in America, we're taking sides, and our side is the side we want to win. So I'm going to go ahead and wrap this up with a couple more images here. Okay. We had a lot of smoke, and that produces some interesting an interesting familiar orangish color on the moon. However, you know, it may draw comparisons for the smoke moon to the blood moon, and I have some pictures of the full smoke moon I took, you know, where the moon is shrouded by smoke in the atmosphere from wildfires. I noticed I had taken a picture of a crescent shrouded by smoke, so it ended up orangish. And you say, if an eclipse of the moon was happening, would it look just like this? Simple experiment. It's like, yeah, well, in order to prove whether it looked like this or not, I got to go find a moon that's being eclipsed. No, it won't. There's a different look to it. When the moon is in the process of being eclipsed, the round shadow of the limb of Earth creates a much deeper cut into the moon than the sun shadow further away. This is about I would say this is roughly there's a little more moon here. But now, if smoke were in the atmosphere, yes, this would take on, you know, a auburn color throughout. And that would be a very interesting photo. But I learned that the two simply won't look similar. So it's nice to have. So I took this image, and it ends up being a comparison of, you know, the moon in two different phases. One's a full moon that's being eclipsed, and the other one is a crescent based on our view. Of course, if we could stand somewhere over here in space, we'd see this part of the moon illuminated and the part of the far side of the moon illuminated and have a completely different looking disk. So regardless of what we're trying to shoot at, I would say having a purpose, you know, having discovery, looking for something that you may or may not realize is there, it always helps. Aurora photography is like that. You always shoot at aurora. You may not see it naked eye, but you shoot to the north and you may capture it, and you can end up getting a beautiful shot. If you are lucky enough, you'll end up having aurora in your shot. If you are If you can see the aurora, it's even better, because then you know where to aim your camera. So with that, I have to leave my bird photo for you, Scott.
Okay, all right.
And
that's
if
a
you
great-
notice, the bird's looking up.
Yes.
And so this this northern male cardinal keeps looking up, and in the interest of advancement of science, and it's not about who's right, it's about it's about advancing our knowledge collectively. The only way we learn anything new, the only thing we're going to be able to learn, whether the same particles of dark matter are in this bird, sorry about that, or are in us, is we have to collectively work on a problem, and maybe drop the individual aspirations. Yes, we can be awarded things, we can have good things happen to us, but and in the end, we should keep looking up and keep striving to surpass what it is that we know ourselves.
Well said, Adrian.
And with that, I hope that's a good way to end the 125th Global Star Party, where a few people come online to share their love of the night sky, share their love of science, astronomy, astrophotography, astrophysics, and everything else in between that this has become. And it's been an honor to be a regular part of it.
Thank you very much. All right. Well, for those of you that are still tuning in here as presenters, I want to wish you a deep amount of gratitude and thanks for being on Global Star Party. And I want to thank our audience that watched from around the world. And for all of you that did not get a chance to watch this program live, we'll be back next Tuesday, starting at 6 o'clock Central Time. And you can interact with us on social media. We're on Facebook, YouTube, Twitch, Twitter, and we're happy to answer your questions. And so, and if any of you out there would like to be on Global Star Party to give a presentation on astronomy, we would be very happy to have you make a presentation segment. So until that time, we are going to say goodnight, and I'm going to wish that our good friend Jack Horkheimer, I always like to quote him as to keep looking up. So good night, and thanks again.